Okay, hopefully it's recording now. So the most common is the size motors and things like that. The equation is power equals F dotted with velocity. So you find the force, so it's the power of a force, right? You take the force and you dot it, do a dot product with velocity. You know what dot products are. It's the force times the velocity times the cosine of the angle between them. That's the easiest way to do it. It's just like work. You know, the force has to be lined up with the displacement. Power, that where the force is backwards and the velocity is opposite, that's a negative power. So that's removing energy. Power is also equal to the time derivative of work, although who cares? It's rarely ever used that way. Now, in general, since I teach system dynamics as well, in dynamics, we're only worried about power, and it's always force and velocity. But in the real world, you'll deal with pumps, and they don't have force, they have pressure, and they have flow rate. You'll deal with circuits, and they have voltages and currents. And so I'm just giving you a little heads up, and you'll learn this in system dynamics. In all systems, there is always two dual variables. One is an effort, and one is a flow. So in dynamics, the effort is forces, torques. Those are the only two that you've seen. Your flows are velocities and angular velocities. Okay, one's a motion and one is a push, if you want to think of it that way. All systems have that. So in electrical circuits, you have a pressure, which is voltage, and you have a flow, which is current. Current is actually something moving, right? It's the electrons moving. In circuits, they taught you it was positive things moving. It's not. It's the negative things that move. Okay, but it's actual motion, just like a velocity is. In the case of a fluid pump, you have pressures and you have the flow of the fluid. Okay, power is always equal to the product of those two quantities. So in circuits, it's voltage times current, and in pumps, it's pressure times flow rate. Okay, and then you have to do unit conversions usually, but it's always that way. And you can always add power. You know, mechanical power and electrical power, it's all basically the same. And then I think for your homework you need a unit conversion, so I'm giving you the unit conversions there. 1 horsepower is 745 watts, and it's the same thing as 550 foot-pound per second. Okay. And then what I'm showing, this is not in the homework, but I always try to give you more than what you paid for. Okay. So for example, here is I'm trying to show you how you would size a motor. So on the left-hand side, what I'm showing is this is a typical torque to speed curve for a DC electric motor. I cut and pasted the thing, so these lines here are just lines on the paper, okay? So what it is it goes like this. If you plot torque of a motor versus the speed's down here and torque is up here. A DC electric motor goes like that. It's a nice straight line. So it's convenient for students to study because it's easy to do calculations. Okay, so let me ask you some questions. If you have a DC motor and you load it up so that it barely moves, so it's operating right here, say, how much power do you have? Very little. Why? You have a lot of torque.
You have no velocity.
You have very little velocity. So at this point, the DC motor doesn't give you any power, or very little. What happens if you let it go screaming? Like this, it's running almost as fast as it can possibly run. You have no power there either. Why not? No torque. Okay, so at the extreme ends of your device, and this happens in most devices. So for example, if you have a pump, on one end you can say, look, I'm going to run the pump and I'm going to set it up so that it gives me the maximum amount of pressure. Then you'll get very little power out of it. Okay, because typically it won't flow. It'll give you a lot of pressure but no flow. Okay. On the other extreme, you say, I'm going to let the thing run and it's going to pump as fast as it can possibly pump. It usually gives you no power because it has no pressure. Okay, no pressure across the pump. Okay, and that's very typical. Okay, so if there's no power on either end, there's got to be power in the middle. Don't you think? I mean, that's why you get motors, right? 1/2 horsepower motor, 2 horsepower motor. You want to get some power out of them. So where would the maximum power occur? How do you know?
Because it's an equal amount of torque and
Okay. In a DC motor, it's true that that's exactly where it occurs. If you had a pump, for example, your pump curves would look something like this. They'll plot pressure versus flow rate, and they usually use Q for flow rate. And those things are typically more like curves. And they'll have a series of curves on a pump. And then what they'll do is they'll show you powers. So they'll draw you maximum power lines like this. The reason that you have multiple curves is what they'll do is they'll say, okay, this curve on the inner curve, that corresponds to using a pipe size of maybe a 1/2 inch diameter pipe. And then the other curve might be for a 3/4 inch diameter, because they don't know what pipe you're going to hook up to their pump, right? And so what they'll do is they make these measurements. And in a case like that where they're curved, it's not always in the middle. Okay, so what you do is you pull up, you buy a pump, and the pump will come with, I mean, if you go to, not Radio Shack, they don't sell pump. If you go to Home Depot or something like that, you buy a pump, they're not going to give you the spec sheet. But if you're doing an engineering job and you're going to buy pumps and you're going to specify pumps for something, it will come with a data sheet, right? And the data sheet will give you a pumping curve. And you look at the pumping curve, and that'll tell you where the maximum power, et cetera, is. Okay, so what I did here, and we'll kind of skip it because it looks like you guys are kind of catching on quick. Over here, what I did is I derived where the maximum power occurs. So all I did was I said power is equal to torque times speed. And I took a derivative of it, said it equal to 0, and it comes out to be, for a DC motor, it's at 1/2 speed. So you're going to get your maximum power when you run your motor at 1/2 speed. Make sense? Okay. All right. The other thing that you'll need for your homework is what efficiency is. Efficiency is the power that comes out divided by the power that goes in. That's efficiency. Okay? Ready to do some problems? All right. Let's do some homework problems. Okay, an automobile having a mass of 2 megagrams travels up a 7-degree slope at a constant speed of 100 kilometers per hour. If mechanical friction and wind resistance are neglected, determine the power developed by the engine if the automobile has an efficiency of 0.65. Okay, what are we going to do? How are we going to do this? Why am I going to do a free body diagram? Right, what I need is I need to know what is the force that's pushing this guy up the incline. That's what I need, right? And then what I'm going to do is I'm going to say, okay, if I have the force that's coming from the engine, what I need to do then is multiply it by the velocity, and I get the power. Make sense? So I'm going to get the force from the engine, what's driving it up the incline. I'm going to multiply it by the velocity. That's going to get me the power that's coming from the engine, okay? And then I'm going to use the efficiency and say, if that's the power I'm getting coming out, because that's what's driving the car, how much power is going into the engine? And I'm going to use the efficiency. That make sense? Okay, so let's do that. Let's do a free body diagram of the car. Here's the car. What are the forces acting on it? Normal. Okay, so let me draw in a dashed line here. That's the slope. 7 degrees. So this angle right here is 7 degrees. All right. So the normal. What else you got? Yeah, it says mg. Okay, good. What else you got? Do what? Yeah, and where does it come from, by the way? Does it just appear? Where does it come from? I mean, it comes from the engine, right? The engine twists the drive shaft twists your differential twists the tires, and somehow that pushes you forward. Where's it coming from? Friction under where? Or where? Where's the friction? From the tires. Now it says no losses, right? Doesn't it say no losses? They didn't say no friction. If you had no friction, if this thing was ice, your tires would spin, wouldn't they? Right? They would spin. You're not losing anything, I agree. You're not losing anything, but the tires are just spinning. Right? Are you going to go up the incline? No. Okay, so what you have is you've got friction between the tire and the asphalt. The tire and the asphalt, right? Is it slipping? No. That's what would give you a loss, is if you punched it and you spun the tires, that's what would give you a loss, because you're burning rubber. You're melting the rubber. You see that? So just because they say no losses doesn't mean you have no friction. You just have enough friction to where the tires don't slide, don't skid. Make sense? Okay, so what's happening is the engine is turning over. It's turning the drive shaft. If it's rear-wheel drive, I have no idea. Drive shaft, well, front wheel does the same thing, right? Okay, turns the drive shaft. The drive shaft turns a differential. The differential then rotates or puts torque on your tires, and the friction between your tire and the road resists that torque. And that friction then is what propels you up the road. Okay, make sense? Okay. So you're going to have a force like this. We'll call it F. That's coming from your engine. And ultimately it comes down to the friction that's on the road, right? And because you don't have any losses, I'm not losing any energy. You remember the bowling ball example that I gave you? Right? And I showed you that, if you're straight like that, there's no, well, what is rolling friction? Remember? It's the deformations, right? Yeah, so like in the case of a bowling ball, you're bending the wood underneath the bowling ball, right? In the case of a wheelbarrow, right, you're pushing down the mud. That's why it's harder to push on mud than it is on the concrete. Remember that? So this is the same thing kind of that's happening here, okay? So you're not losing any energy from squashing the tire. Well, that's kind of hard to believe, but okay. It's just homework problem. Any other forces on this? No? Okay. Travels up the slope at a constant speed. So what's the acceleration? Zero. Okay. Can you find the force? How are you going to find the force? Okay, very good. Yeah. What I'm going to do is I'm going to sum forces up the incline. Right? And you've already done it in your head and you got the answer. No problem with that. Okay. I'm going to go ahead and sum them up. The incline is going to be the positive direction. So we'll say this guy is plus X. And what I have is F minus mg. Is it sine or cosine? I don't remember. Is it a lot or a little? Should be a little, right? So just kind of a small slope. Sine of 7 is a lot smaller than cosine of 7. So it's probably the sine. You can also draw a line or a triangle. Sine of 7 degrees equals what? Mass times acceleration up the incline. How much is it? 0. Okay. So you can find F. F equals mg sine of 7. So you got that number. What's the power? What's the power that's delivered to the car? What's the definition of power? Very good. Force times velocity. So what's the velocity? Oh, it's 100 kilometers per hour. Okay, so the power equals mg sine 7 times 100 kilometers. That'd be 100,000 meters per hour, 3,600 seconds. I think I did the unit conversion right. Isn't that meters per second?
Yes.
Huh? Where's the dot product? Okay, which way is the force? Straight up the incline. Which way is the velocity? Straight up the incline. What's the angle between those two? 0 degrees. What's the cosine of 0? 1. So it's the magnitude of the force, magnitude of the velocity, times the cosine of the angle between them. So which is 1? Good point. Keep me honest. Okay, so that's the power. That's the power that is being used by the automobile. That's the power that's coming out of the engine, right? What is efficiency? Efficiency is 0.65 is the efficiency. That's equal to what?
Power out.
Power out divided by power in. The power in is always bigger than the power out. Otherwise, we'd be creating energy and we'd be selling that and we'd be making lots of money. We wouldn't need engineers. Okay, right? So the power out is always lower than the power in. You put more in because it wastes some. Okay, so power out. How much is the power out? It's that number right there on the diagram, right? So I'm going to call it P. That's the power that comes out of the engine because that's what goes into the car, right? Divided by the power in. So how much power is going into the engine? Could you find it? I think so, right? So it's this number P divided by 0.65. That's the power that goes into the engine. Okay, let's talk about this. Is this a hard problem? What was hard about this? Oh, by the way, let's back up. How do you know it's a power problem? Well, okay, yeah, but I can give you efficiencies on every single problem on the final exam. Yeah, it says determine the power developed by the engine. Ah, you need power? It's a power problem. That's the only reason to do a power problem, okay? Because, you know, you can do all of the problems. Well, I should be careful. You can't do all the problems using power, but you can do a lot of them using power. But it's really complicated, and it's mind-bending and confusing. You don't want to, right? The only reason to use power is because somebody wants it. And why would anybody want it? Well, I'd like to know how big an engine do I need to drive this car up the hill at 100 kilometers per hour, right? How big of an engine do I need? Well, how much horsepower do I need, right? So that's why I would want to do it. You're going to have a senior, you're going to be successful, I know it, and you're going to get to senior design. And about half of you are going to want to get a motor and put on something to make it do something. Half of you will. And you're going to come to me and say, how do I size this motor? And I'll say, didn't I teach you about power? That's how you'll do it. Right? You figure out what the power is that you need to drive your car up a hill. Throw in a safety factor because you'll say, well, I've got friction. And then you're going to say, I need 2 horsepower. Okay, that's the motor you need. Okay? Got it? All right, so how do you know it's a power? Not because I gave you an efficiency, because I think I'll do that on every single problem on the final. Because it says, what's the power? That's why you use power, because you want to know the power. That's the only reason. Questions? You want to do another power problem? Yeah.
The power that we got there, it's the power in.
That is the power that is required to drive the car up the hill, right? Yeah, that's the power the car needs to go up the hill. And how do I know it's that way? Well, because they told me there were no losses. Because if the car had wind resistance and friction and had a loss, it would have an efficiency as well. I'd put this in, but I wouldn't get this out. Why? Well, because, you know, for example, you know, if this is what goes into, from the engine, goes into the car, but the car has some losses, then the car's not going to give me the output the same that went in. It's got an efficiency. What does that mean? It won't go as fast up the hill. That's what it means, right? Because the power out would be this force times the speed. And if this is what goes in, and let's say it's 50% efficient, you have a 50% efficient car because you got friction in the bearings, you got, you know, rubbers squash in, whatever it is, right? Wind resistance, your kids have got their hands out the window, you know, whatever, right? That's causing an inefficiency. So let's say it's 50% efficient. Then I put this power in, thinking I'm going to go 100 kilometers an hour up, right? But I only get half of it coming out and being used by the car to drive it up the hill, right? Will I get the F? Yes, you'll get the F. Will you get the speed? No, you won't get the same speed. It'll go slower. Make sense? Right? Just like back here on this other, right here. Come on. Right here. You see, what'll happen is if this is your car engine right here, that's your car engine. Okay? You need it's got some inefficiencies. You need this much force to drive up the hill. You have to have that, or it won't go up the hill. Then what'll happen is, based on the energy or the power, you're going to get a certain speed. Right? So if you have an inefficiency in the car, you're going to deliver the power from the engine. Some of that power is going to be wasted in the losses, and what you're left with is force times velocity that will drive you up the hill. That's what's left over. You got to have the F or you won't go up the hill. So the motor will slow down, right? According to the curve, the motor will slow down so until it gets the force that you need. And when it gets the force that you need, whatever that speed is the speed you're going to go up the hill. Right? Does that make sense? Right? You throw in a bunch of friction on the car, make it less efficient, it's not going to go up the hill as fast. Right? Understand? Is it possible that you need more force than your motor can provide? Yes. Try riding your bicycle over Trans Mountain. Maybe you can do it. Can I? Not anymore. Not anymore. It's a combination of too much mass and not enough force. Right? Get the idea? Okay. You want to do another problem? Yes.
Why did you divide the velocity by 3600?
It says it was kilometers per hour, and I wanted it to be meters per second.
And the mass? You wanted it in kilograms?
Oh gosh, yes. The mass is 2 megagrams or something, so that would be 2,000 kilograms. So yes, my bad.
So the mg sine 7 is it the P in or the P out?
Okay, so this F right here, is that the force in or the force out? That's the force I need to drive up. That's not power.
No, but the mg sine 7 was 100,000.
Okay, this one. Okay, what is this power? Can you help him? He's asking, what is that power? Look, I'm taking the car, right? I'm saying this is the force that the car needs to go this fast up the hill. Isn't that the power that the car has to have? That's the power that goes into the car. How much of that power is lost by the car? None. None. The engine loses 65%. So you got, let me draw you a kind of a diagram. What you have is you got an engine here. And you got gasoline going in. The gas has got power or energy, right? And it goes in at a certain rate, and it's burning at a certain rate. So there's your power. It's energy per time. So there's your power going in. How much comes out? I'm going to call it P prime. That's how much comes out. Okay? It comes out of the engine. Where does that power go? Right, it goes to the car, it goes to the drivetrain, it goes to the gearbox, it goes to the everything that's connected up to those tires, making it move. Is there inefficiency in the car? You betcha there is, but this problem said to ignore that. Didn't it? It said ignore all the inefficiencies in the car. It said to do that, didn't it? So if I have P prime going in, how much do I have coming out? P prime. Whatever goes in's got to come out. Or else it gets turned into heat, gets turned into other forms of energy. I can't destroy it, but it'll get converted into other kinds of energy. Okay, now, what is this? This is what I need to go up the hill, isn't it? Did I lose any in the car? Okay, then this guy right here is what comes out of the engine. You agree? What is P prime? P. Isn't that P? That's the power I have to go up the hill. That's the power I got to have to go up the hill. And because the car is 100% efficient, that's what I need going into the car, coming out of the engine. I need that amount coming out of the engine. If that's what I have coming out of the engine, and the engine is 65%, what do you got to have going in? You got to have more. P prime divided by 0.65. Let's change the problem a little bit. Let's say your car is 80% efficient. Okay, your car is 80% efficient. Got it? What does that mean?
We have to calculate P prime.
Okay, right. 80% efficient. Okay, what that means is, well, it's not 0.8. Okay, it's 80, 0.8. That's your efficiency, 0.8. That means the power out of what? What's the efficiency of? The car? Okay, power out of the car divided by power in of the car is 0.8. What's the power that comes out of the car?
MG sine 7.
Exactly. This is the power that comes out of the car. That's the power that comes out of it. How do I know? Because it's going, I watch it. It's going up a 7-degree hill at 100 kilometers an hour. That's the power that's coming out of the car. I can see it. Boom, there it goes, man. Right? Or argue with me if it's not. Is that the power coming out of the car? Okay, what is being delivered to the car? It'll be the P divided by 0.8. That's what's going into the car. Right? So what's going into the engine? P over 0.8 over 0.65. That's what's going into the engine. Make sense? If not, I don't know what to tell you. You look like you disagree, so argue with me. Or wake up. No. He looks like, no, man, you're lying to me. Yeah, let's do another problem. Does this make sense? You have to just remember, where's it going in, where's it coming out, what's it equal to, and back yourself back up. I don't think they're hard, it's just confusing. Don't you agree? They're just kind of confusing.
What are the units?
The units are watts. Power is energy per time. So for example, we think of horsepower, right? Car people think of horsepower, and that is special unit. Watt is a Newton meter per second is a watt, right? So a watt, yeah, joule, okay, is a Newton times a meter divided by a second. A Newton meter is a joule. I don't know how specific you want it. A joule is a Newton meter. So if you have joules, but the basic units for power is force times speed. So it's Newton times meter per second. It's pound times foot per second. And then horsepower is a conversion off of that, etc. So it's force times speed is the unit, the basic unit for a power. Okay? How about this one? Oh man, come on. Okay, elevator E and its freight have a total mass of 400 kilograms. Hoisting is provided by the motor and the 60 kilogram block B or C. If the motor has an efficiency of 0.6, determine the power that must be supplied to the motor when the elevator is hoisted upward at a constant speed of 4. All right, is this a power problem? How do you know? Because it says find the power, okay? That's how you recognize it's a power problem, okay? I don't know of anybody that on purpose, uses power to solve dynamics problems. The only time that I know, and yeah, I don't know everybody in the world, okay? But the people I know, they'll use the others because they're easier to get the solution. But if somebody says, I want the power, okay, then this is a power problem. Okay, so how am I going to do this power problem? See what's happening? It's going to go at constant speed. They give me the speed. They want to know the power that goes into the motor. Okay, so here's the diagram. There we go. What are you going to do? why a free body diagram?
Because you got a mass.
So,
And forces.
I have masses in almost
So
everything.
you can sum the forces.
What is it I want?
Powers.
I want power. Okay, power is equal to force dotted with speed. Now they told me the speed, right? So what am I missing? The force. That's why I'm drawing a free body diagram, because I want to know the force. And the only way I know to get forces is to draw a free body diagram and some forces. Do you know another way? Okay. What force am I looking for? The force between the crates and the elevator? The force in that cable on C? You want that? Or what force, really? What's the motor pulling on?
On the pulley.
It's pulling on the rope, isn't it? That you see the rope between these pulleys? This rope, right here? Isn't it pulling on this rope right here? So really what I want is I want that tension. Because that's what the motor's pulling on. He's pulling on that, and he's pulling it in at a certain rate. Isn't he? Okay. So what I'm looking for is what's the tension in the cable, and how fast is that rope going in. The elevator's moving 4, but how fast is the rope moving? Got it? So those are the two things I want. How hard am I pulling on the rope? And how fast is that point moving? Got it? Okay. How are you going to find the tension in the cable? I'm going to draw a free body diagram. That's what I'm going to do. Okay? So, what free body diagram do you want? What do you want in the system? How about I do something like this? I'm going to draw a circle around here. I'm going to cut it like this. Everything inside the circle is in my free body diagram. Is that good? I've got two masses inside there, so if I have accelerations, I'm in deep trouble. Right? Because I'm going to have to take the EMA and, ooh, it's going to be a little ugly. Do you have any accelerations? Oh, thank goodness. Okay, this will be an easy problem then. All right, so let's sum forces. Okay, what forces do I have to draw? MG of what?
Well, no, of the masses of the system.
Of the system. Can you help me? Is it mass C or mass E? Huh? I could do two free body diagrams. If it's easier for you, we'll do two free bodies, right? You say, okay, there's an elevator and there's a C. You want to do that? Okay, we'll do that then, all right? Hey, you asked for it, man. Or I can do both. I'll do both. But here, I'm going to do this one. Okay, now is that one easier? Okay, gray matter has to, okay, let's draw that free body diagram. What does he look like? Okay, MC times G, and a tension, we'll call it T1, because rope 1. And then I've got the elevator, right? You're going to let me get away with that? Didn't I teach you anything?
Oh, that's the tension.
What do you say when I do something stupid like that? Hey, stupid. Maybe not like that, but why is that stupid?
The tension there.
No. Why is that stupid? That force doesn't belong in there. Why not?
It's outside.
It's outside. Is the E inside the free body that you wanted me to draw? No, he's outside. And he's between what? The earth. Is the earth in there? That force does not belong there. Right? You know this. Don't let me get away with stuff. Okay, let me erase it. That's a free body diagram. You agree? Okay, don't let me get away with that. Okay, let's do the other free body diagram too. I think somebody had a question. You have a question.
On, since you're trying to find well, obviously you know the mass of the cart, right, the elevator?
Yeah.
And then you know the mass of C, couldn't you subtract them and just do one free body diagram?
Yeah. That's what I was gonna do. Well, I think what it does is it eliminates, I'm not sure what advantage you would have, but that's what I did it. I did it at home, I did it like that. I put them both together. You know, you know, what he's saying is, hey, it makes sense to me to put them both in there. That's fine, and I'll show you how to do that. Otherwise, you separate them out. You say, why deal with the complexity? Well, then separate it out. Okay, let's do the other free body, right? Here we go. What mg goes in this one? The elevator. Why not C? Because it's outside, right? It's always been that way. So this is mass of the elevator times g. Okay, now, on this guy, what else is in there, right? Let me, let's see, I know you all told me not to use yellow, but this is the only, well, let me see if I can get a red pen. Come on. Yeah, there we go, red. Okay. So now we'll use red. Okay, so I'm going to circle this guy right here. That's the system. So what other forces do I have in here? Yeah, I have T1. I have how many of them? One right there. Okay, so 1 T1. What else do I have? I have 1, 2, 3. We'll just call them T's. Is that okay? Okay, how many unknowns here? Do you know T1? You do? How do you know it? Okay. Was it given? I don't think it's given. Yeah, but what you're thinking is you're going to sum forces, right? Okay, fine. So don't count that equation then, because you've already used it to get T1, right? So you either count the equation and count the unknown, or you don't count either one. Okay, how many here? T? Do you know T? No? Okay, so can we solve them? Okay, T1 is what? Do it in your head. He did it. He did it in his head. What's T1? Tension is always equal to the weight, right?
No, so force.
Tension is not always equal to the weight. Tension, right, sum forces, minus mcg equals mass times acceleration. What's the acceleration in this case? In this case, 0? Okay, now, when it's 0 acceleration, that's when the tension equals the weight. Okay, so you know T1, right? You know T2? Or excuse me, T? 3T plus T1 minus mass of the elevator, G, equals 0. Can you solve for T? Okay, so now I've got T. Now all I need is the speed of the rope. How am I going to find that? Rope equation, right? How many degree of freedom? I should count this first. How many degree of freedom is it? Okay, just because I look at you weird doesn't mean you're wrong, right? It means make sure you're right. You know, 1 degree of freedom. Why? Because the elevator can move, right? Okay, count 1. Hold the elevator still. Can anything move without breaking? Okay, 1 degree of freedom. What does that mean? It means if I give you 1 dot, you can find all dots you want. Well, not a triple dot, right? But you know, right? It's been a whole semester. Okay, are you given a dot? Yeah, the elevator's going up at 4. Okay, then I need to relate one to another. How do you relate them? Special points. Is this a special point problem? Is this a vector loop problem? What is it? It's a rope. Okay, so what rope do you want? I see 2 ropes. Which one do you want to use? Yeah, the one that's got on the motor, right? That's the only one I care about. Okay, can you write the length of that rope? Length of the rope equals. You tell me. I'm going to shut up. You tell me what it is. What's the length of the rope? 3x ME. What's ME? Okay, so the distance to the elevator, we'll call it XE. Is that good, everybody? Okay, so the distance from the roof to the elevator, we'll call it XE. Now, what's the length of the rope? 3 of those? Plus or minus some constants, right? Okay. 3xe. Take a derivative, plus a bunch of constants. You're right, plus a bunch of constants. Take a derivative, what do you get? Don't tell me 0 equals. Is L constant?
No.
It is? No, the rope is being pulled in, right?
Yeah, it's not that.
So, I don't know. It's L dot. Equals 3. What's this guy? What's VE? Velocity of the elevator? Do I know it? What is it? It's 4. So L dot is 12. So what does that mean? Well, actually, I should do it like this, right? L dot is, XE is a negative. I should write it like this, XE dot. Take the derivative, 3XE dot. What's XE dot? The magnitude is 4. Is it plus or minus? Is XE getting bigger or smaller? Smaller? It's going up, right? So this guy right here is a minus 4, isn't it? Okay, so this is a negative 12. Right, the L dot is negative 12. Is L getting bigger or is L getting smaller? Getting smaller. And you knew that, right? Okay. What's the power? Power of the motor. Power coming out of the motor.
Magnitude of the force.
It's the force times what? Velocity. And what's the speed that I'm going to use? What's it pulling on? The rope. How fast is the rope moving? Here's a little red dot on the rope. Okay, let's draw a little red dot. There's a little red dot right there. What's the force on that dot? T, right? Isn't it T? How fast is that red dot going? 4 or 12? He's going 12? Okay, what's the power at that red dot? T times 12. Right? That's T times 12. So what's the power coming out of the motor? T times 12. So the power out is 12T. What's the power going into the motor? I have efficiency of what? 0.6, okay. So 0.6 efficiency equals, what is it? In over out? Out over in, out. 12T, that's what comes out of the motor. What goes into the motor? PN. Can you find PN? Now, is it a hard problem or just kind of confusing? It's confusing. It's not like the numbers are hard. But what you have to do is say, well, look, you know, what's the motor pulling on? The motor is pulling on the rope. All right? What's the tension? What force am I applying? And how fast is it moving? Not the elevator. Right? Not the elevator. I want to know what's the power from the motor. So what's the motor pulling and how fast?
How would you do?
How would I do?
The volume of the entire thing?
Of the entire thing? Yeah. I think if you do, you end up with an extra unknown with the tension on this guy. This is what I was going to do. This would be mass of the elevator G and mass of the C G. And then I would have tension 1 and 3 tensions up. Right? My mistake. That won't give me, I need 2 free bodies. When I did it at home, I did it in my head. And it didn't work, obviously, when I write it down. So clearly I was wrong. Everybody makes mistakes. Especially me. Okay. But if I did that, I would suddenly, just like I did now, I'd say, whoops, too many unknowns, T and T1. And then I'd say, well, okay, I'll draw another three-body diagram. And I would have been embarrassed, like I am now. Okay, yeah.
Were we finding the velocity of the elevator?
No, we're finding the velocity of what? Tell them why the rope.
So that's where the tension force is.
Yeah, because, if I'm looking for the power of the motor, I say, well, what's the motor doing? He's pulling on the rope.
Yeah.
And how fast is he pulling the rope? I don't care about the elevator. Another way to do it would be to come in and say, okay, I tell you what, I want the power that's going into the elevator. Well, what's pulling on the elevator? 1, 2, 3, right? And then this guy, but then you'll notice that the energy here is kind of confusing. But you go 1, 2, 3 tensions, and what's the velocity? 4. So I'd have 3T times 4. It'll be the same power. But I think that's more confusing.
And you get the negative 4?
Yeah. Well, why did I get a negative 4? What's XE? XE is measured from where to where? And isn't that a positive number right there? Okay. Now, when I take a derivative, which I did here, I was getting sloppy. I was trying to do it in a hurry. When I take a derivative right here, it's XE dot, right? Okay, so then I ask myself, is XE getting bigger or smaller? Elevator's going up, so XE is getting smaller, right? That's why I put in a minus 4. And what do I get? Negative 12. Well, what does the negative mean? Well, L dot is a negative 12. Is L getting bigger or smaller? Smaller. So it kind of works out. But you don't need the positive negative. You just, because the guy is pulling on you this way, right? He's pulling up and he's coming up, isn't he? So he's doing positive power. And you can see I was sloppy. I was just going to say 12, and then I thought, I bet you they're going to catch me on that one. So I went back and slowed down and said it's really a negative 12, right, because the rope is getting smaller. But what's happening? I've got this dot. I'm the motor. I've got this red dot on the rope, and I'm pulling it up, and it's coming up. So I'm doing positive power. Does that make sense? Right? So I'm doing positive power. So do whatever you need to for the pluses and minuses, but you're putting in power. Okay.
Would power in always be positive?
No, if you want to slow something down, you're going to take power out of it. Right? So you got this Mack truck,
Oh, gotcha.
and I want to stop it. And so I'm going to push on it. Right? I hope it doesn't run me over. I'm going to push on it, and it's coming at me, and I'm taking power out of it. Friction, wind resistance takes power out. That's a negative power.
Like engine braking?
Engine braking takes power out of the car, right? I guess it eats it up in friction. Not quite sure where it goes. I know what it is. I hadn't thought about where it goes. I guess it goes into the, you downshift and you ease the clutch out, so you're burning up your clutch. Okay, any other questions about power? Okay, that's all I was going to cover. All I was going to do now is just review. So if you got a question, you got something that's bugging you for the final, let's talk about it.